Hello everyone, we are from Group 2 of BNQ20503 Material Engineering Technology, and today we'll be presenting our group project on memory shape alloy. My name is Terence Kenevun, AN240149.
I am Joanne Goh Jia Eun, matrix number AN240159.
Hi and Assalamualaikum warahmatullahi wabarakatuh. My name is Noifah Sofia. My matrix number is AN240119.
Assalamualaikum and hi, my name is Muhammad Aidil Mukis bin Satria Anwar. My matrix number is CN250395 and I will present about detailed review of the material.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aifah binti Azizul Azli and my matrix number is CN240282.
Hi, my name is Muhammad Nur Hakim bin Azizi. My number matrix is CN250391.
Advanced materials are specially engineered materials with improved properties such as strength, flexibility, and corrosion resistance. They play an important role in modern industries including healthcare and manufacturing. Nitinol is an alloy made from nickel and titanium. Nickel provides strength and corrosion resistance, while titanium offers high strength, low weight, and excellent biocompatibility. Nitinol is widely used in medical stents because of its unique properties. First, it has shape memories which allows it to return to its original shape after deformation. Second, it exhibits super elasticity, enabling it to bend and recover without permanent damage. These characteristics make nitinol ideal for minimally invasive medical procedures. A stent is a small tube placed inside a narrow blood vessel to keep it open and maintain blood flow. Nitinol stents can be compressed during insertion and then expand automatically once inside the body. They are also corrosion resistant and compatible with human tissues, making them safe for long-term use. In conclusion, nitinol is an important advanced material that combines the advantage of nickel and titanium. It shapes memories, super elasticity, and biocompatibility make it an excellent material for medical stents and other healthcare applications.
At the atomic scale, nitinol functionality relies on a fully reversible solid-state phase transformation. It transitions between a high symmetry cubic austenite phase and a lower symmetry monoclinic martensite phase without any permanent atomic slippage. Thermodynamically, this transition minimizes Gibbs free energy because the energy path for deforming the stent differs from its recovery path. It creates a non-linear hysteresis loop. For biological development, we ensure the final transformation finish temperature (AF) occurs right at 37 degrees Celsius, utilizing the body's own thermal energy as the actuator to expand the stent. Mechanically, the stent utilizes superelasticity to withstand constant arterial pulse pressure without suffering permanent structural damage. However, our numerical models must account for tension compression asymmetry as the microstructures experience completely different stress states on their inner and outer boundaries during bending. Finally, because raw nickel is highly toxic, biocompatibility depends on a protective surface passivation layer of titanium dioxide. These microscopic chemical barriers prevent dangerous nickel leaching into the bloodstream, maintaining both patient safety and long-term structural integrity.
So welcome. Today, for my part, I will be talking about shape memory alloys or SMA. Today, we are going to exploring the distinct behavior mechanism, mechanical properties, chemical structures, and electrical profiles of these incredible smart materials, with a particular focus on nitinol and copper-based alloys. To begin with, let's establish what defines an SMA. Unlike traditional metals, SMAs undergo a reversible solid-solid diffusionless phase transformation. They essentially transform their crystal structure without atoms diffusing over long distances. Today we focus mostly on nickel titanium known as nitinol and copper-based alloy. So the microscopic performance of these smart materials is dictated by thermal or stress-induced transformation between two key phases: the low temperature martensite phase, which is soft and malleable, and the high temperature austenite phase, which is hard and rigid. Understanding this shift is the key to mastering SMA design. The classic mechanism is one-way shape memory effect. When the alloy cools into its twined martensite phase, it can be easily deformed. After removing the load, it remains deformed. Only when heated above the austenite finish temperature does it remember and recover its rigid pre-programmed shape. Unlike the one-way effect, the two-way shape memory effect remembers a shape at both low and high temperature, moving back and forth without external stress. However, it requires intense thermomechanical training, delivers only half the strain, and degrades much quicker, limiting its use in major products. Now, let's review superelasticity and hysteresis. Superelasticity occurs above AF. The alloy can deform up to 10% and spring back instantly upon unloading, with no heat required. Hysteresis, shown by delta T formula, determines the response rate. Narrow is great for high-speed robotics, wide is ideal for pipe joints. Mechanically, SMA pack a massive punch. Their work density is 10 joules per cubic centimeter, about 25 times more than standard electric motors. Nitinol delivers an actuation stress of up to 700 megapascals, and its Young's modulus more than doubles when transitioning from martensite to rigid austenite. Despite their strength, SMAs face fatigue and environmental limits. Accumulating microdislocation degrades their memory. To ensure long fatigue life, engineers restrict the functional strain to 3 or 4%. Also, watch out for hydrogen levels above 120 ppm, trigger severe hydrogen embrittlement. When we look at the chemistry of SMAs, the surface structure is key. Nitinol is near equimolar and forms a highly stable passive titanium dioxide layer, giving it outstanding corrosion resistance and biocompatibility. However, we must limit nickel ion leaching below the toxic threshold to 1 to 9 micrograms per millimeter. The electrical properties of SMAs are particularly exciting for mechatronics. The resistivity increases when transitioning from martensite to austenite. Since this change is highly linear, we can use resistance feedback to perform sensorless position control. We can also integrate thin film SMA into photodiodes.
And today I will briefly discuss the advantages and disadvantages of nitinol. One major advantage of nitinol is the shape memory effect, which allows automatic movement and makes it useful in medical devices and actuators. Another advantage is superelasticity, where nitinol can bend or stretch significantly and still recover its original shape. This property is useful in orthodontic wires, eyeglass frames, and cardiovascular stents. Nitinol also has excellent corrosion resistance because it forms a protective titanium oxide layer. In addition, it is biocompatible, meaning it is safe for use inside the human body, especially in implants and surgical instruments. It also has good fatigue resistance, allowing it to withstand repeated movement without failure. However, ethanol also has some disadvantages. The material and manufacturing costs are high, machining is difficult, and its properties are sensitive to temperature changes. In conclusion, ethanol is an advanced material with many useful properties, especially in engineering and medical applications, despite its higher cost processing challenges. That's all for me. Thank you.
Now, recent scientific works on the chosen material. Nitinol-shaped memory alloys have long been the gold standard for medical stents, but as medical science advances, good enough is not option anymore. Today, a new wave of scientific research is pivoting towards structural modification, nano-engineered coatings, and total anatomical customization. The goal, unparalleled durability, ultimate biocompatibility, and stents that adapt perfectly to the human body. It starts with the blueprint. Traditional cross-braided nitinol stents are strong, but they face a major enemy, long-term material fatigue and structural rupture from constant bodily movement. So recent biochemical studies have introduced a game-changing evolution, which is the cross and hook braided design. Quantitative testing shows that adding this tiny structural hook modification delivers significantly greater bending flexibility and elevated radial stiffness, all while maintaining optimal tensile resistance. This directly minimises device fracturing and protect delicate tissue during repeated dynamic physiological movement. But changing the structure is not enough. We also have to change the surface. A modified nitinol poses a dual risk, the potential leaching of nickel ion into surrounding tissue and localized blood clotting or thrombogenicity. To combat this, researchers have developed graphene-coated nitinol. Graphene acts as an impermeable barrier that suppresses metal ion leaching and boosts corrosion resistance. Even better, it attracts serum albumin absorption, which dramatically lowers thrombosis rate and accelerates vessel healing. Additionally, scientists are incorporating amorphous calcium phosphate and magnesium hydroxide nanoparticles into protective polymers. This clever chemistry neutralizes acidic byproduct and maximizes long-term tissue compatibility. Finally, we are leaving the era of one-size-fits-all uniform tubular geometries behind. By combining three-dimensional reconstruction with computational fluid dynamics (CFD), biomedical engineers can now design patient-specific non-tubular stents. Recent trials have successfully validated spherical nitinol mesh stent mapped directly from a patient's unique anatomical data. Because nitinol possesses a continuous self-expanding force, these custom shapes adhere perfectly to irregular biological margins without slipping, outperforming traditional balloon expandable counterparts. So, by rewriting the rules of geometry, nanotechnology, and personalized data, modern science is transforming nitinol from a simple medical tool into an intelligent, harmonious extension of the human body.
And that is all for our presentation. To wrap it up, I'll summarize the core insights of our research on nitinol in medical stent engineering. Our study highlights that shaped memory alloy like nitinol stands out as a vital class of advanced smart material because of their unique ability to undergo reversible solid-solid phase transformations. And as we've discussed, this fundamental behavior, shape memory effect, and superelasticity are what make nitinol the cornerstone of modern stent design. They allow biomedical devices to be heavily compressed for minimally invasive delivery and then reliably expand to support biological pathways once they reach their destination. Beyond their mechanical memory, these alloys offer essential biocompatibility and corrosion resistance through the formation of stable titanium dioxide passivation layer, making them safe for long-term use inside the human body. However, as engineers, we must maintain a careful balance. As we have seen there are critical limitations that we must address, such as manufacturing complexity, long-term functional fatigue, and risk of hydrogen embrittlement. Looking ahead, the future of SMEs is incredibly promising. By integrating the recent innovation we explored, such as the cross and hook braided designs, the graphene-engineered protective coatings, and the 3D computational modeling, the next generation of medical devices will be safer, more durable, and increasingly tailored to individual human anatomy. That is all for our presentation. Thank you.